Hello all. I'm very happy to report that I have received many comments and requests about uploading more mathematics papers, and especially the mechanics part, right? Okay. So this is the second paper I'm going over, and this is Mechanics M3, and it's from January 2026. And as you might recall, the other paper I uploaded is also Mechanics M3, also from 2026. And the reason is that now Edexcel outputs two papers. The one is called M3 and the other one is called M3A. Okay. And another thing that you might have noticed right now is that I changed the settings of the pen in hopes that the handwriting improves, but we will see how this goes. And also, I went over some Mechanics M1 and M2 papers, so I'm looking into them. So hopefully soon I will upload videos related to that. But anyway, I talk a lot, so let's dive in and see how this goes. Okay. So question one: a particle P of mass half a kilo moves along the positive x-axis under the action of a single force of magnitude F newtons. The force acts along the x-axis in the direction of x increasing. When P is x meters from the origin O, it is moving away from O with speed the square root of 8x to the 3 halves minus 4 meters per second. Find F when P is 4 meters from O. Okay, so let's use a clean page so we have space to work. So we have that the mass is half a kilogram. Okay, and force F is applied to this particle. Okay, this is our origin O, and this is the x-axis. Okay, in this direction. And let's put the particle here, and let's draw the force with green. So that's the force, that's the particle of mass m. Okay, and we are also given that the velocity as a function of x, which I put in parentheses, is the square root of 8x to the 3 halves minus 4 meters per second. Okay, and for those of you who are watching my videos for a long time, please let me know if these settings for the pen work better, and whether my handwriting looks better. Okay, so what's the force? Force is equal to ma, right? So m dv over dt, right? Because acceleration is the first derivative of velocity, but the velocity is given in terms of x, so we have to rearrange things a little bit. So we have to write dv over dx times dx over dt. Okay, and you can easily see that if I delete this dx, I retrieve dv over dt. Okay, so we can proceed. But now dx over dt is simply v. Okay, so the force is given by mv dv over dx. So now we have to find the derivative of the velocity with respect to x. So let's call this equation 1, and let's find the derivative down here. dv over dx is 1/2, right, times 1 over the square root of 8x to the 3 halves minus 4, and then times the derivative of whatever is in the square root. In this case, the quantity in the square root is this function, 8x to the 3 halves minus 4, and the derivative of that is simply let me see, wait, why am I confused? Yes, it's let me delete this one over there so I can work. So it's 3 halves times 8 x to the 1/2, right? So I think this works. Okay, so we can delete this and make this a 4. So 3 times 4 is 12 over 2 makes 6 x to the 1/2 over the square root of 8x to the 3/2 minus 4. Okay, if this is not clear, ask me in the comments and I will provide answers. But I hope this is clear. Okay, I'm checking to see if I made any mistakes. No, so let's call this relationship 2, and let's use another clean page. Okay, so from 1 and 2, we find that f is m times the square root of 8x to the 3/2 minus 4, okay, times the derivative we just found, which is 6x to the 1/2 over the square root of 8x to the 3/2 minus 4. Okay, so this is equal to the square roots actually cancel nicely, and we are left with this very simple expression 6m times x to the 1/2, and we are asked what the force is when x is equal to 4. Okay, so it's 6 times the mass, 0.5, times the square root of 4, which is 2. Okay, so we have 6 times 2 is 12, times a half, 6 newtons is the answer. Okay, so long problem, but I think straightforward. So we are ready to move on to the next problem. Okay, problem 2. Question number 2. A spacecraft S of mass m moves in a straight line towards the center of the Earth. The Earth is modeled as a sphere of radius r, and S is modeled as a particle. When S is at the distance x, where x is larger than or equal to the radius of the Earth, and the distance x is measured from the center of the Earth, the force exerted by the Earth on S is directed towards the center of the Earth. The force has magnitude k over x squared, where k is a constant. So in part A, we have to show that k is m times g times r squared. So let's start with the first part and then see how the things goes. So clean page. Let's actually draw the situation. So we have a circle, k, which represents the Earth. This is the center, say. Is it the center? Kind of, okay. Maybe let me use a dot, because I don't want you to get confused with the variable x. Okay, so that's the center of the Earth. Okay, so the radius is r, and the particle is over here at the distance, let's say, let me see, at the distance x. Okay, so now let's try to solve problem A. Okay, so the force is given as k over x squared. Okay, we have to find that constant k, and to find it we will use a trick. Okay, so at the surface of the Earth, right, at the surface of the Earth, right, x is simply equal to r. And what is this force? And the force is just the weight, right? And the force is equal to the weight of the particle. Okay. In other words, F at x equal to r is m times g. Okay, so m times g, where g is 9.81 meters per second squared. M times g is k over r squared. Therefore, k is mg r squared. Okay. I was supposed to make a box. I don't know how the iPad came up with this shape. Okay, let me fix it. Okay, good. So part A is done. So let's use another clean page. So we now know that the force is mgr squared over x squared. Okay, so we made some progress towards solving this problem. Okay, Now, in part B, so when S, again, S is the spacecraft. And by the way, I've seen lots of questions about spacecrafts, yes, in all the units of Edexcel, and now in the mathematics papers as well. And I think it has to do a little bit with the fact that NASA is sending Artemis. I mean, it already sent Artemis to space and stuff like that. Probably, I don't know. Let me know what you think in the comments. So, when S is at a distance 3r from the center of the Earth, the speed of S is v. Assuming that air resistance can be ignored, find, in terms of g, r, and v, the speed of S as it hits the surface of the Earth. Okay, and this awards 7 marks, so it's a difficult question. Okay, and by the way, the same principles for those of you who are watching my videos. I generally recommend that you try to spend as many minutes in a problem as is the marks that it awards. So in this case, it's 9 marks, so it should take about 9-10 minutes, okay? So you stay on track and on time, okay? Now let's try to solve it. Okay, so this is part B. So basically, what we will do is the following. We will write down F is equal to mass times acceleration, right? And what is the F? I mean, we are going to use Newton's second law, in other words, okay? So the force is mg r squared over x squared, right? And it's equal to m times dv over dt. Okay, so we are encountering the same issues we had before. With taking the derivative of velocity with respect to time, but the velocity is given with respect to distance, so we have to convert that. But we get this nice cancellation. Okay, so let's move on. I mean, the mass cancels. So we will write, I will bring dv over dt to the left-hand side. So, and I will write dv over dt as follows: dv over dx times dx over dt. Okay, it's the same trick as you did before. And the right-hand side is going to be gr squared over x. Okay, and now dx over dt is simply v. So we now have v times dv over dx is equal to gr squared over x. And now we need to introduce a negative sign for actually dx over dt is going to come with a negative sign. Excuse me for not mentioning. Okay, so there is a negative sign there. And the reason is simply because if you go back to the scheme, x increases in the positive direction. So x is positive in this direction, but the velocity, the particle is falling in the opposite direction than x, okay? So the velocity increases in the opposite direction that x increases. Therefore, in our case, v is actually minus dx over dt, okay? Because x increases to the right and v increases to the left, okay? I hope this makes sense. If it doesn't, ask me in the comments. So in this step over here, when we write dx over dt over there, we have to write dx over dt as minus v, okay? So now we will do the following. So v times dv is equal to minus gr squared are constants, so we can pull them outside of the integral, and then we have the integral of dx over x, okay? And we can integrate v as well, okay? So v dv integrates as v squared over 2, and then by the way, what did I do here? So it's x squared, guys. I'm sorry, I don't know why I lost my concentration. Excuse me, forgive me about that. Let's move on. Okay, so the integral of minus 1 over x squared is simply 1 over x. Okay, so this is equal to g r squared over x, and then plus a constant. Okay, so we actually found an equation for the velocity, but we have that annoying constant, but we are given one condition. We are given that at x equal to 3 times r, in the wording of the problem, we know that the velocity is equal to, let's write v, okay? So the velocity is equal to that capital V, this one that they mentioned, so this one, okay? So I write it as v to distinguish from v, okay? I hope this makes sense. So using that condition into this equation, let's call it equation 1, and this is condition 2. So we get that v squared over 2 is gr squared over 3r. So r cancels, plus c. So c is equal to v squared over 2 minus gr over 3. Equation 3. And using 1 and 3, by the way, did I use other numbers before? No. Okay. So from 1 and 3, we have that v squared over 2 is equal to gr squared over x plus this v squared over 2 minus gr over 3. So at x equal to r, the velocity we get is v squared over 2 is equal to gr squared over r. So that r squared is cancelled with the r in the denominator, plus v squared over 2 minus gr over 3. So v squared over 2 is 2gr over 3 plus v squared over 2. So finally, the velocity when it reaches the surface of the Earth is the initial velocity squared plus 4gr over 3, because we are multiplying with these 2 in the denominator, okay? So that's the answer, okay? And this was problem 2, okay? Not too hard, but you need to be careful with, especially in the parts where you use the initial condition to find C. I'm talking about this point over there. You have to be careful with the substitution down there. And the integration is straightforward, I think, okay? I mean, it's not too hard. So this was problem 2. Let's move on to problem number 3. Problem 3, a particle P is moving in a straight line with simple harmonic motion about the fixed point O as center. When P is a distance 0.02 meters from O, the speed of P is 0.3 meters per second, and the magnitude of the acceleration of P is 0.5 meters per second squared. Question A, find the period of the motion. Okay, let's start with that, and then we will come back and read the other parts, okay? So we will use a clean page. By the way, notice that these versions that they call version A of a unit do not give you any space to write. But if you go to the back of the paper, they give you space over here. So I don't know. These papers are a little bit of a mystery, I would say. I don't know why they put them out, but it's extra material for you guys to study. So I think it's good to go over them. Okay, so let's solve this. So part A, before we do part A, let's make a small scheme showing the situation. So this is the oscillator, okay? So this is the center O, and we are told, what are we told again? When P is at a distance of 0.02 meters from O, the speed is 0.3 and the magnitude is 0.5. Find the period of the motion. So let's say that this is the distance of 0.02 meters. Okay, and the velocity there is 0.3 meters per second, and the magnitude of the acceleration is 0.5 meters per second squared. This is what they say, right? the magnitude of the acceleration. Okay, so for part A, and let me know in the comments that you actually know this, but I'm gonna prove it anyway later. So what I'm saying is that A is omega squared times x, okay? Actually, it's minus omega squared times x because it's an oscillation. So if we take the magnitude of this is going to be equal to omega squared times x. And using this, we can find the period. So omega squared is a over x, the magnitude of a over x. So this is equal to 0.5 over 0.02, and the units are meters per second squared, and then we have meters due to the distance in the denominator. So this has units of seconds to the minus 2, which makes sense because omega squared has units of seconds to the minus 2. So omega squared is 25 seconds to the minus 2. It's actually radians per second squared, but okay, let's move on. One comment for those of you who are new to these videos, when I solve physics problems and I substitute quantities into a formula, I put all the numbers to the left. So numbers go to the left and units go to the right. This makes it easier to work and cancel units and stuff like that. Okay. So now omega is the square root of that. So omega is 5, let's say, radians per second, but omega is 2 pi over the period. So that's equal to 5. So t, the period, is 2 pi over 5. So we find 1.26 seconds. Okay, and that's the period, which we can write as 1.3 seconds. So the period is done. Let's go back and read problem B. The amplitude of the motion is a meters. Find the value of a. So we need to find the amplitude pretty much, okay? So the amplitude would be, I don't know, this extreme over here and this extreme over there. So this is going to be a, and this is going to be minus a. Naming it a is a poor naming convention because you can easily get confused with the acceleration, but okay, we will work with what we have. So let's move on. So basically, I don't know, write me in the comments, but v squared is omega squared times a squared minus x squared. I don't know if this can be taken for granted, but I'm gonna actually spend a minute or so to actually prove this for those of you who need some extra lessons. So if you start with an oscillation, so an oscillation has a displacement x equal to a, the amplitude, times sine omega t. It can be cosine omega t, it can be sine omega t plus some initial phase phi, etc. It doesn't matter, okay? It works the same way with any type of oscillation. So I'm going to write in parentheses. It can be cosine omega t, it can be sine omega t plus phi, whatever. Any of these also work with what I am about to show, okay? So if the displacement is that, then the velocity is dx over dt, or in other words, it's omega a cosine omega t, okay? And then the acceleration is, of course, the first derivative of the velocity. So it's minus omega squared a, and then sine omega t. Okay, so we get these really nice formulas pretty much. So we will take these first two, actually, we don't need the acceleration. And let's do the following. So we can write x as, we can multiply x with omega. So omega x is alpha omega sine omega t. So I haven't done anything, I just introduced omega both in the left-hand side and the right-hand side. And then the velocity is simply a omega cos omega t. Okay, now if I square this, I will have omega squared x squared is equal to a squared, or alpha as I called it earlier, omega squared times sine squared omega t. And if I square this, I will have v squared is a squared omega squared cos omega squared t. And I can add these things. In the left hand side, I will have v squared plus omega squared x squared is equal to a squared omega squared and then sine squared omega t plus cosine squared omega t, which adds to 1, okay? And I use this square brackets to distinguish from the curly brackets, okay? And not the curly, the regular brackets, whatever, okay? So we get that v squared is omega squared times a squared minus x squared, okay? So I I actually proved the relationship that I told you that we need to use to solve this problem, okay? But in case this cannot be taken for granted and you need to prove it, this is the proof, okay? So let's move on. All you have to do is to plug numbers into that equation. So we have v squared. V is 0.3 squared, okay? And then omega squared is 25, we found it earlier, times the displacement squared, minus 4 times 10 to the negative 4, which is x squared, because they give us that when the particle is at 0.02 meters, okay, the velocity is 0.3. So this is what we will be using, okay? So now all you have to do is to solve for a squared. So 3.6 times 10 to the negative 3 is equal to, let me see, a squared minus 4 times 10 to the negative 4. So a squared is 3.2 times 10 to the negative 3. So a is 0.06 meters. So we find that a very round number. Very nice result. Okay, done. So part B is done. But there's a part C. So let's go back and read it. Okay, so part C says find the total length of time during each complete oscillation for which P is within 1/2 of an amplitude meters from O. Okay, it should be from O. That's a typo, I believe. So let's go back. We use another clean page. So C, first of all, okay, let me do this, and then I'm gonna explain what I'm doing. So we will take that x is a sine omega t. Okay, so if we plug a halves, okay, if we plug a halves as equal to a sine, and then omega t is what we actually need to find, we get that omega t is so we basically have to solve the trig equation sine omega t. Okay, let me not skip this extra step. Sine omega t is 1/2, which means that omega t is the inverse sine of 1/2. Okay, so omega t is pi over 6. So time is pi over 30 seconds. Okay, so at time pi equal to 30 seconds, the object makes it to the amplitude a halves. Okay, so by the way, omega, for omega, what did I use here? Give me a second because I'm confused. Yes, omega is 5, right? 5 radians per second. So basically here I kept using omega, but omega is 5, okay? So, and here. I'm sorry if I confused you. Okay, so what we found is the time that the particle needs to go from the origin to a over 2 for the first time. Okay, so it will need pi over 30 seconds to go once, and then it will need another time to go back there and come back here, and then it will take another pi over 30 seconds to go back to the origin. Then it's going to take another pi over 30 seconds to go to minus a over 2, right? And then it's going to go all the way to a, which is the amplitude, and then come back, and then spend another pi over 30 seconds to go back to the origin. So in total, this is what we need, okay? In total, it's going to take, let's call it t total. T total is the time it will take 4 times what we just calculated. So 4 pi over 30 seconds is the total time it will take, okay? And I have the mark scheme in front of me. Let me double check that I didn't mess something up before we move on. So this is question 3, right? So question 3, yeah, the answer is 2 pi over 15. I mean, if we simplify this, we get 2 pi over 15 seconds. But I hope my explanation is correct. So basically, the logic is to find how much time it takes to go from the origin to a over 2 one time, which is pi over 30, and then multiply by 4, because in an oscillatory motion, it's gonna spend its time between minus a over 2 and a over 2 4 times that time. Okay, now question number 4. A light elastic string has natural length 5 meters and modulus of elasticity 20 newtons. The ends of the string are attached to 2 fixed points A and B, which are 6 meters apart on a horizontal ceiling. Therefore, in this scenario, the string is stretched by 1 meter, okay? So a particle P is attached to the midpoint of the string and hangs in equilibrium at a point which is 4 meters below AB. Question A, calculate the weight of P. Let's start with that one. It's easier when you draw a scheme, so let's do that. So first of all, let's write down what we know. So this question 4, we know that the length of the string is 5 meters. Therefore, half the length is 2.5 meters. You will see why I'm writing that in a moment. And the modulus of elasticity lambda is 20 newtons. Great. So initially, we have the string attached between points A and B. So this is our string. Okay, great. Don't know why it deleted it. Okay, so 6 meters. So that's the initial situation. Later, we still have the points A and B, okay, but we hang a weight. Okay, let's draw it down here. So we hang a weight of yeah, it's unknown, so we have to find it. Let's call it weight is times G, okay? Even though I think they just ask for the weight, so we don't need that. So let's keep it as weight. Sorry for the hesitation. So that's weight. And then our string is gonna stretch in a weird way like this, okay? And it basically, the mass is in equilibrium because there is a force F from the right side of the string, and an equal force F from the left side of the string, Okay, I'm losing my trail of thought for some reason. I'm getting old, guys. So anyway, so let's connect these lines A and B. Okay, so basically, we are told that this distance is 4 meters. Okay, so 4 meters. And this distance is 3 meters, right? And the extension of the string, because the force is equal to lambda times whatever the stretch is over the length of the string, right? So this is x, and it's the extension of the string, and you will see why. Basically, it's a 3, 4, 5 triangle, but we need to use Pythagoras to prove it. So for the extension, we have that x squared is 3 squared plus 4 squared. So x is 5 meters. Okay. And we basically, let me think. So that length is x, and it's 5 meters. Therefore, the right hand side of the string is stretched by 2.5 meters and the left hand side by 2.5 meters as well. And why is that? Because half the length of the string is 2.5 meters. So if x is 5 meters, then the whole length of the string becomes 10 meters. Therefore, the extension, the total extension is 5 meters, right? And half the extension is, the extension is 5 meters. I'm sorry. Okay, so I hope you are still following. So we have to find this angle theta. And why is that? Because we have, for equilibrium, we have the fact that the weight should be equal to 2 times cosine of theta times lambda times x over L. And why is that? Because we need this component of the force, and this component is F cosine theta. And we need it twice because we have a force from the right hand side and a force from the left hand side. So let's write 2 times F times cosine theta. Okay, now cosine theta is equal, from the scheme, from the drawing we made, cos theta is 4 over 5, right? 4 over 5. So let's plug everything in. So the weight is 2 times 4 over 5 times lambda, which is 20, times x, which is 5, over, let me think, over 5. Okay. So the length of the string is 5 meters, right? And the reason why we use x as 5 meters is because we use the x we just calculated, okay? So, yeah, it's correct. I'm sorry, I got confused a little bit. So, basically this is equal to, 5 cancels, and then we have this thing evaluating to 32 newtons, right? So 2 times 4, we can do this. So 4 times 4 is 16 times 2, 32. Okay, I hope it's clear. So basically F is lambda times x over L, but x is the extension of the string, which is 2.5, right? Which is 5, and then the length of the string is 5. Okay. So this is the answer I found, and it agrees with the mark scheme. All right, now let's do part B. Calculate the particle is now raised to the midpoint of AB and released from rest. Calculate the speed of P when it has fallen 4 meters. So this is a little bit of a complicated problem. So we will use another clean page. So let's draw the situation again. So AB, and we have this point down here, which is 4 meters. Okay, so this is 4 meters. And we are told that this is the particle P, and we are told that we take the particle all the way up here and then release, and we have to find the speed. Okay, so we will use conservation of energy pretty much. Okay. We will take the gravitational potential energy to be 0 at the lowest level. Okay, so that's 0. We will call this point 1 and then point 2. And the story is that the total energy at 1 should be equal to the total energy at point 2. Okay, what's the total energy at let me think, the total energy at point 1 is going to be lambda times, let's call it x prime squared over 2L from the elastic energy of the string, plus the kinetic energy 1/2 mv squared, plus 0 because GP is 0, okay? And this should equal the total energy at 2. What's the total energy at 2? The kinetic energy up there is going to be 0. So 0 is the kinetic energy plus mgh, where h is 4 meters, plus lambda times the extension of the string up there over 2L, and it's the extension squared, I'm sorry, okay? So let's plug numbers in. So we have 20 times the extension at the point 1. So this is what I call x prime, okay? Maybe it's easier if I write it like this. Okay, maybe it's clearer if I write it as x1 squared, and let's write this as x2 squared, x2 squared. Okay, so we have 20 times x1 squared, and x1 is the extension, which is 5 squared, right? And this is because at the lowest point we calculated earlier that the total length of the string becomes 10. Therefore, the extension is 5, okay? So when it's stretched at the lowest point. So 20 times 5 squared over 2 times 5, and then plus 1/2. And then the mass is not given to us, but we're given the weight, so we can use that. The mass is equal to the weight over 9.81, which is g, right, times v squared. And this is equal to 20 times the extension at point 2, which is simply 1 squared, over 2 times 5. And why is it 1? Because at point 2, the length of the string is 6 meters, but the natural length is 5, so the extension is 1, okay? So that plus mgh, so mg is 32 times 4, okay? So we get that 16v squared over 9.81 is equal to 80, so v is the square root of 80 times 9.81 over 16, which is 7 meters per second, which is the answer. Okay, a little bit of a complicated problem, but using conservation of energy saves the day. So this was problem 4. So we are ready to move on to problem 5. By the way, one of the thoughts I have is to create separate videos just showing one question at a time. So for example, for this paper, there are 7 questions in total. Therefore, I can have a video for question 1, a video for question 2, question 3, all the way to 7, and then the full walkthrough. Okay, it's easy to do. I mean, you can edit the full length video and upload those separate questions as well. Let me know if that's something that would be useful, because I'm experimenting with many ideas with my channel, so I still haven't settled in what this channel should be. So I'm experimenting, so let me know your thoughts. Okay, question 5. Up top, they say that in this question, you must show all stages of your working. Solutions relying on calculator technology are not acceptable. And I guess they mean that you cannot evaluate an integral by using a calculator. You have to show that you can actually calculate the integral by hand. Okay, figure 1 shows the finite region R, which is bounded by part of the curve with equation y equals to sine x, the x-axis, and the line with equation x is equal to pi over 2. A uniform solid S is formed by rotating R through 2 pi radians about the x-axis. So we get surface of revolution and also a solid of revolution, I guess. This is how it's called, which is going to be something that looks like a cone, but not a cone, really. Okay. Using algebraic integration, question A, show that the volume of S is pi squared over 4. Okay, let's start by doing that. So there is no scheme in this case. I mean, it's just the math of the problem. So the volume is equal to pi times, actually, let me move this a little bit down so I can work. Okay, so let's move it there. Okay, great. So the volume is pi times the curve squared dx integrated, and we are integrating x from the bounds, right? 0 to pi over 2. Okay, I mean, this is 0, this is pi over 2, so we are integrating this region. Okay, so we basically have to evaluate the integral pi, and then integral from 0 to pi over 2 of sine squared x dx. Okay, which we can write as, okay, pi is constantly there, being annoying. So integral from 0 to pi over 2. We reduce the square by using I think these formulas are known. I hope they don't ask you to prove them. I mean, 1 minus cosine of 2x over 2. Let me know in the comments if you actually have to prove this, because if you have to prove this, the game becomes different, okay? But I'm assuming you can use it, okay? So that's how we can write it. So now pi acquired the company of 2 in the denominator. So we have pi over 2, okay? And then the integral of dx minus again pi over 2 and the integral of cosine 2x dx, and the bounds are the same as before, of course. Okay, so we have pi over 2 and then x from 0 to pi over 2 minus pi over 2, and then the integral of cosine of 2x is sine of 2x over 2, and this goes from 0 to pi over 2. And we get a very nice cancellation because you will see, okay? So we have pi over 2 times pi over 2 minus 0, and then minus pi over 4, and then the sine of 2 times pi over 2 is pi, minus sine of 0, both of which are 0. So we get a very nice result for the volume as pi squared over 4. Okay, this is a nice result. Okay, so part A is done. Part B, find in terms of pi the x-coordinate of the center of mass of S. Okay, again we will need to use standard formulas. So for part B, we have x, and I'm going to denote it like that for the center of mass, is equal to pi, and then the integral of 0 to pi over 2 of x times sine squared x dx. Okay, I think I went a little bit too fast. Maybe let's write it like this. So it's going, the center of the x center of mass is going to be pi times the integral from 0 to pi over 2 of x y squared dx over the volume that we just found. So okay, let's keep going. So pi, and then the integral from 0 to pi over 2 of x sine squared x dx, and then the volume is pi squared over 4. So this pi cancels, and the 4 goes in the numerator pretty much. So we have 4 times the integral from 0 to pi over 2 of x sine squared x dx. And if you reach my age, you just stick this into Mathematica and it spits out the answer in a second. But unfortunately, you have to prove it. So let's take this integral and calculate it in a clean page. So we have the integral from 0 to pi over 2 of x sine squared x is equal to x, and then we use exactly the same idea as before, 1 minus cosine of 2x over 2 dx from 0 to pi over 2, which is equal to 1 over 2 integral from 0 to pi over 2 x dx minus 1 half the integral from 0 to pi over 2 of x cosine of 2x dx, which is equal to 1 half x squared over 2 from 0 to pi over 2 minus we will integrate by parts, so we will cast this into minus 1 over 4, then the integral from 0 to pi over 2 of x, and then d of sine 2x. And then the d of sine of 2x is cosine 2x times 2, therefore that's why I made that, I set this equal to minus 1 over 4. Let me know if what I'm doing is actually what you're supposed to do, because I never actually taught this lesson of Mechanics M3, so I'm doing what I think it should be done in problems like this, but let me know if I'm doing a good job. So let's move on. So this is equal to 1 over 4 and then pi squared over 4 minus 1 over 4, and then we have x sine of 2x from 0 to pi over 2, which is the integral by parts, minus the integral from 0 to pi over 2 of sine of 2x dx. Okay, now this cancels, okay, because we are again dealing with the sine of pi, which is 0, and then minus something times the sine of 0, which is also 0. Okay, so we are left with we will need another clean page. We have pi squared over 16 plus what did I do? Let me think. Yes, we have minus 1 over 4 times minus. It becomes plus 1 over 4. And then the integral of sine of 2x is minus cosine of 2x over 2 from 0 to pi over 2. So we get pi squared over 16 minus 1 over 8. And then we have cosine of pi minus cosine of 0. So we finally get pi squared over 16 plus 1 over 4. And this is because this is equal to minus 2. Okay, so the x of the center of mass is, let me think. So it's 4, the center of mass is 4 over pi times pi squared over 16 plus 1/4. Okay, yields, okay, I confused myself. It's tough to do mental math on an iPad. So it's 4 times, 4 times pi squared over 16 pi plus 4 over 4 pi, right? Okay, so let's simplify this to make it 4 pi. So it's pi squared plus 4 over 4 pi. And that's the final answer that matches the mark scheme. Okay, difficult problem in terms of math. I mean, you have to perform a few integrations, but straightforward. Okay, and that was question 5, and we are ready to move on to question 6. Excuse me. Okay, let's move on. Okay, question 6. The path followed by a motorcycle around a circular racetrack is modeled as a horizontal circle of radius 50 meters. The track is banked at an angle theta to the horizontal, where sine theta is 3 over 5. The motorcycle travels around the track at constant speed. The motorcycle is modeled as a particle, and air resistance can be ignored. In an initial model, it is assumed that there is no sideways friction between the motorcycle tires and the track. Using this model, A, find the speed in meters per second of the motorcycle. Okay. So let's, in this case, we do need a scheme. So this is problem 6. So you have to use your imagination a little bit to imagine the track. Okay, and this is the bank of the curve. Okay, this angle is theta, and this is our motorcycle. Okay, we assume it to be a particle. So it has a weight, right, that drags it down. Okay, so that's the weight. And this is the reaction from the floor, which is perpendicular to the banked curve, pretty much. And it undergoes circular motion in, you have to imagine the track, the center of the track is here, okay? So this is the radius, pretty much, of curvature. Even though they don't say it, this is what it looks like in, if you imagine it in 3D, okay? So let's keep that. So what I'm trying to say is that you have to analyze the forces with respect to the centripetal force, which is in this direction, okay? So we basically have to analyze R into a component that points this way and a component that provides this centripetal force that I'm talking about. Okay, this angle now is theta. Why is that? Because this side is perpendicular to this side, okay? And then this side is perpendicular to this side. Therefore, the inscribed angles, in this case theta and theta, are equal. So this component is r cosine theta. And in other videos, I always say that if a component touches physically the angle theta, in this case, that's the angle, and it touches that component that I'm drawing down there. That component is r cosine theta, and this component is r sine theta. Okay, and after all this math, we now have to use the equilibrium in the y direction, because the motorcycle is not moving up and down in this direction. Therefore, r cosine theta is equal to m times g. Okay, and then r sine theta provides the centripetal force, therefore it's equal to m v squared over the radius. Okay, so if we divide these two, this r cancels, the m cancels, and we have 1 over the tangent of theta as equal to r times g. By the way, let's name this r, okay? I named it capital R earlier, but it can confuse you with r, the reaction force. So r is the radius of the curvature, okay? And so it's r times g over v squared. I hope I didn't go too fast, but what I did is that we have g over 1 divided by v squared over r. So this is equal to r times g, right? Times, over v squared. Okay. So what are we trying to calculate again? We have to calculate v, right? So we have to find the tangent of theta. We are given, what are we given? The sine of theta is 3 over 5. Okay, so using that, so we will use the fact that sine squared theta plus cosine squared theta is 1. Therefore, cosine squared theta is 1 minus sine squared theta, which is 9 over 25. Therefore, cosine squared theta is simply 16 over 25. So cosine of theta is 4 over 5, Okay, let's change the page. So the tangent of theta is simply sine of theta over cosine of theta. The sine of theta is 3 over 5 and then over 4 over 5, right? So the 5 cancels. So we have 3 over 4 is the tangent of theta. So we can go back to this formula. Let's call it 1. We don't need to, it's okay, because maybe I will need that later. So let's use that formula. We have 1 over tangent of theta is equal to, let me see, r times g over v squared. Therefore, v squared is r times g times the tangent of theta. Therefore, v is the square root of r times g times the tangent of theta. So v is r is given as 50 meters, right? Yes, the radius is 50 meters, okay? So 50 times 9.81 times 3/4 yields 19.18 meters per second, which is the answer. So yeah, that's the speed we need. So let's read the second part of this question. In a refined model, it is assumed that there is a sideways friction. The coefficient of friction between the motorcycle tires and the track is 1 over 4. It is still assumed that air resistance can be ignored and that the motorcycle is modeled as a particle. The motorcycle's path is unchanged. Using this model, B, find the maximum speed in meters per second at which the motorcycle can travel without slipping sideways. So let's use a clean page. Okay. So we will need a new scheme because now the situation has changed. Okay. So this is still the floor, the banked curve, same as before. Theta, the motorcycle is this particle over there. The weight is again down, of course. We still have the reaction force, right? So that's R. But now we also have the friction, and the friction is in this direction. And the reason is because the motorcycle will tend to move in this direction. Therefore, the friction is in this direction, okay? If this doesn't make sense, please ask me in the questions. Sorry, please mention it in the comments and I will provide a better explanation. But again, the motorcycle undergoes circular motion with respect to the center of the track, which is somewhere here. So this is R. So we have to analyze the forces. So now we have, again, like before, for the reaction force, we have this component, which is R cosine theta, okay? And again, this angle is theta. And we have this component, R sine theta. But this is not the only component that provides centripetal force, because we now have the component of the friction. And now this angle is theta as well, okay? And the reason is that basically the green line and the floor are parallel, right? And so using Thales principle, this angle and this angle are the same, okay? So that angle is theta, therefore we have a component of the friction F sine theta in the same direction as the weight, and we have a component of the friction in the centripetal direction, so we have F cosine theta pointing towards the center of the track. So we are told that the friction is 1/4 of the reaction force, pretty much, right? And now the equations of motion are as follows. So r cosine theta, in the y direction we have balance again because the motorcycle is not moving up and down. So r cosine theta is equal to the friction times sine theta plus the weight. And now we will plug in the fact that r is unknown, the cosine of theta is 4/5, and this is equal to the friction, which is 1/4 times r, times sine theta, which is 3/5, plus the weight. Okay, so we will find an expression for the reaction force, pretty much, using this methodology here, which we will use later to find the velocity. Okay, so we have r/5 times 4, and then I bring this component to the left hand side, so minus 3/4 is equal to weight, right? So r, so let me see, so r times let me think, times 13/20, right? So yes, wait, something confused me. So 4 is 16/4, so minus so 13/4, yeah, 13/20 is correct. Okay, excuse me for that. Okay, it took me a moment. So this is equal to the weight, okay? So r is 20/13 times the weight. So the reaction force is 20/13 times m times g. Okay. Now, for the centripetal motion, we have that we have F. So let's write it centripetal motion. These two components added, pretty much, are equal to mv²/4. So F times cosine theta plus r times sine theta is equal to mv²/r. Now, F is, let me think, F is 1/4 times r times cosine theta, which is 4/5, plus r times sine theta, which is 3/5, is equal to mv²/r. Stay with me. I promise this works out. Okay, so I will bring mv² to the left hand side. So mv²/r is 4 times capital R, which is the reaction force, over 5. And now we can use what we just calculated. So we have mv²/r is equal to 4/5 times 20/13 times m times g. So m cancels. So the problem kind of solved itself. So v² is, we get a few cancellations, and this works out to be 16/13 times, and the reason is this, pretty much. So 16/13 times r times g. So another clean page. So v is the square root of 16/13 times r times g. And r is still 50 meters, so we have 16/13 times 50 times 9.81, which yields 24.57 meters per second, which is about 25 meters per second. So just by including friction, we go from, what was the result earlier? From 19 meters per second to 25. So a significant improvement in the maximum speed we can have. Okay, difficult problem, but again, straightforward. The trick is to analyze the forces correctly and to find and use the trigonometry correctly. Okay, so this was question 6, and we are ready to move on to question 7, which is the final question in this paper. Okay, question 7, the last one, as you can see. So the total for the paper is 75 marks, and I believe you have 2 hours. Let me think, let me see. Because I commented on how much time you should spend on each problem. So you have 1 hour and 30 minutes, so 90 minutes. The paper awards 75 marks. So yeah, that's a good rule still. So about a minute per mark. So, but let's go back to question 7. A particle of mass m is attached to one end of a light rod of length L. The other end of the rod is attached to a fixed point O. The rod can turn freely in a vertical plane about the horizontal axis through O. The particle is projected with speed u from a point A, where OA makes an angle alpha with the upward vertical through O, as shown in figure 2. The particle moves in complete vertical circles. Given that cosine of alpha is 4/5, show that u is larger than or equal to the square root of 2GL/5. All right, so we need to use conservation of energy. Let me try a thing that I never tried before in these past paper walkthroughs. Can we cut this, actually copy this and move? No? We can take a screenshot. Okay, cool. And then let's do copy, and let's start a clean page. And can we paste it here? Perfect. Okay, this is exactly what I wanted. I never tried this before, but it works. Okay, let's move it there. Beautiful. So let's use our pen. So we need to use conservation of energy. So basically, we will use conservation of energy between the point up here. Let's call it point 1, and call this point 2. Let me redraw. Let's make this 1. Can we move it? No. Okay, it's done now. Okay, so let's draw a horizontal line through point A. Okay, so basically, this is part A. Actually, question 7 of part A. Okay, I feel like I made a discovery, and I'm pretty sure you're gonna be laughing, guys, from the other side of this video, because you guys are younger and you use these things more often than me, so you're more familiar with technology. So I feel like an idiot, but okay, let's move on. So the total energy at point 1 is equal to the total energy at point 2. Okay, what's the total energy at point 1? It's 1/2 times m times v squared. Actually, before we do this, let's do some trigonometry a little bit. So first of all, let's call this x. Let's call this distance x. Okay, so cosine of alpha is equal to x over L, right? So x is L times cosine of alpha, and you will see how that is useful in a moment. So let's go back to the equation of conservation of energy. So at point 1, we'll have 1/2 m times the speed squared, so the final speed squared, so let's call it v squared, plus m times g times this distance that we call y, so mgy, okay? And we take the gravitational potential energy, we take GPE to be 0 at point 2. So at point 2, the only energy we have is kinetic, and it's equal to 1/2 m times u squared, which is our initial velocity, okay? Now, for the particle to barely make it to point 1, its velocity, so v squared, is going to be 0. Okay, so if it barely makes it, that's going to be 0, provided that 1/2 m u squared is larger than mgy, the potential energy of the particle at a distance y from 2. Okay, but now what is y? Y is L, the length of the rod, minus x. What is x? From the trig we did earlier, x is L cosine alpha. Okay, so let's combine these two and use a clean page to find that, by the way, the m cancels. Okay, so we have u squared has to be larger, right? So this m cancels, forgive me for cutting it, larger than 2gy. So u squared, oops, has to be larger than 2g, and then y is equal to L minus L, and then the cosine of alpha is given as 4 over 5. So u has to be larger, u squared has to be larger than 2gl over 5. So u has to be larger than the square root of 2gl over 5. Okay, so done. Part A is done. Okay, now part B. As the rod rotates, the least tension in the rod is T and the greatest tension is 4T. Show that U is the square root of 17 over 5 times G times L. Okay, so this is a little bit more difficult now. Let's do the same thing again and copy this because we will need it. Okay, so this is the part we need. So screenshot again. Copy. This made me really happy, guys. I don't know why. So let us get the clean page again. Press. Come on. Okay, paste. Let's make this large. Okay, and move it there. It looks pretty. Okay, let's get the pen back and let's get going. Okay, so we need several things now. First of all, let's redefine where the potential energy, the GP is 0. So let's define that the GP is 0 when the particle is down here. When the particle is down there, it has the maximum tension, right, from the rod. So T max, and then the weight, of course, points down. And when it makes it all the way up there, it gets the minimum tension. So we have T minimum and we have the weight pointing down. Okay, so U is the same as before. So let's write the equations of motion for the particle at the top. So let's call this top and let's call this bottom. So let's start with the bottom and then work our way up, literally. Okay, so the centripetal force is T max minus the weight, which is m times g, is equal to m and then v max squared over L, right? So let's call this equation 1. And let's do the top. Okay, at the top we have T minimum plus mg is equal to m times v minimum squared over L. So this is equation 2. Okay, and let's work out the energies now. We will use conservation of energy. So, and we will do so twice, okay? One with respect to the top and one with respect to the bottom. So you will see what I mean. So energies. So we have 1/2 m times u squared. So if we take GP to be 0, then at point A, actually, okay, I went a little bit fast. What I'm trying to do is to use the conservation of energy between the point A and the bottom, and then the point A and the top. Okay, so E total at point A is equal to E total at the bottom. Okay, so what's the total energy at the point A? It's 1/2 m u squared, and this is the u we try to calculate, plus the potential energy. What's the potential energy? mg times the height. What is the height? The height is L, right? Plus that quantity x that we calculated earlier, and x, I remind you that x is L cosine A. So L plus x is simply L plus L cosine A. Okay, and at the bottom we only have kinetic energy, guys, right? No potential energy, because we defined that we defined the bottom to have 0 potential energy. Okay, so that's equal to 1 half m v max squared, and we cancel the masses. I mean, we get this nice cancellation. Let's call this equation 3. And then similarly, we have the total energy at A is equal to the total energy at the top. Okay, so we will take the total energy with respect to the bottom though. Okay, so we have that 1 half m u squared, right? Plus, it's the same as before, plus m g, and then L plus L cosine of alpha is equal to 1 half m times v minimum squared plus the gravitational potential energy with respect to the bottom, where we define the potential energy to be 0. This is important, by the way, okay, to stay consistent when you calculate total energies. Otherwise, this is not going to work out. Okay, so what's the distance of the top from the bottom? 2 times L. So the gravitational potential energy is mg times 2L. I hope this is clear. The masses cancel, and we call this equation 4. Okay, then we have 2 additional equations. We are told that if the minimum tension is T, which we call equation 5, then the maximum tension is 4T. So this is equation 6. Okay, stay with me. I promise this works out in the end. So let's start the clean page again. Okay, so using 5 and 1, sorry, and 2, let me think, we get that T, so from equations 2 and 5, 2 and 5, we get that T is equal to m times v minimum squared over L minus mg, and then using equation 6 and 1, okay, so 6 and 1, we get that 4T, which is T maximum, is m times g plus m v max. Let's write it in a symmetric fashion. Let's okay, excuse me for that. We get m v max squared over L plus m times g. Okay, so basically we will plug, now we will do the following. Let me remind myself what I did a few days ago. Okay, so we will plug, so what we will do is to plug this into that. Okay, so basically, yeah, we will plug this equation into there. Okay, so we will get 4 times then 4 times mv minimum squared over L minus m times g is equal to mv max squared over L plus m times g. Okay, and these masses cancel now. We get this nice cancellation, and we have, let me think, we will move Vmax to the left hand side, so we have 1 over L times 4V minimum squared minus V maximum squared being equal to 5mg. Okay, and we will call this equation 7. Okay, and from equation 3, so equation 3 is the equation for the energy, we get u squared over 2, okay, plus 9gl over 5 is equal to V max squared over 2. Therefore, V max squared is u squared plus 18 mgl. Oops, how did I introduce the mass again? So 18 g times L, excuse me, over 5. So this is equation 8. And now from equation 4, we get that u squared over 2 plus 9gl over 5 minus 10gl over 5 is equal to V minimum squared over 2. Therefore, we have that V minimum squared is u squared minus 2gl over 5, which is equation 9. And now from equations 7, 8, and 9, we can finally write that 1 over L times 4u squared, okay, which is, so I'm basically plugging V minimum squared into equation 7. So 4 times u squared minus 8gl over 5 minus u squared minus 18gl over 5 is equal to 5g, okay? So we get that 3u squared minus 26gl over 5 is equal to 5gl, okay? So we get that 3u squared is 51 over 5 gl. So we can simplify that to 17. So we get that u is the square root of 17 times gl over 5, which is exactly what they asked us to find. If we go back, and this was a long problem, guys, okay? I will give you that, but this is exactly what they asked us to find. Okay, so the trick here, especially for part B, was to use conservation of energy wisely, okay? So we took GPA to be 0 down there. By the way, you will find exactly the same result if you took GPA to be 0 up there, but you had to stay consistent when using, so the total energy there has to be consistent with whatever the choice of where the gravitational potential energy is 0 is chosen to be. Okay, so in our case, we chose it to be in the bottom. I don't know, it just sounded more rational for some reason. Okay, this was a long and difficult test, I have to say, okay? Let me know what you thought about it. Let me know if these videos are useful, if I should keep making more videos. The channel is still not profitable, but hopefully at some point it will become profitable. I'm a little bit tired and I have many things to do, so I don't know when the next video is going to be, but I'm working on things, especially mechanics M1 and M2, so we'll see. Please like and subscribe. Please leave a comment that you made it to the end of the video, if you did make it to the end of the video, and see you in the next one, guys. Bye.